Hello, this is Professor Mitchell, and I'm going to be talking to you today about the graphs of sine and cosine functions. This PowerPoint is largely from our textbook, which is Blitzer Pre-Calculus 5th edition, as you can see on your screen. However, I have made some tweaks to it and added a few things that I think you might find helpful. So let's get started. Our objectives here are going to be to understand the graph of y equals sine x, understand the graphs of variations of y equals sine x, and then the same objectives for cosine. Understand the graph and graph variations. So what you're looking at here is the table of sine and cosine values for quadrant 1. It's really important to know this table. From this table you can evaluate any trig function in any quadrant by using reference angles and also by using the quotient identities for tangent and cotangent and the reciprocal identities for secant and cosecant. Notice the nice pattern in the sine values. They go from 0 to 1, 0, 1 half, square root of 2 over 2, square root of 3 over 2, up to 1. And then the cosine values they're the same exact values in the reverse order, which makes it easier to remember. Some features of the graph of y equals sine x. So what you're looking at here is a table. This table represents the entire unit circle. The first part of the table from 0 to pi over 2 is right from the table that you were just looking at, going from 0 to pi over 2. That's in quadrant 1. And you can see that as x increases from 0 to pi over 2, y increases from 0 to 1. And then going through quadrant 2, from pi over 2 to pi, y decreases from 1 to 0. So these values are all taken from the unit circle. And when you plot all these points, what you end up with is this nice curve. This is one period of the graph of the sine function. And you'll recall from an earlier section that the sine function is periodic. So if we were to start looking past 2 pi, this curve would just repeat. It would look exactly the same, going from, say, 2 pi to 4 pi. And now the graph of the cosine function. Similarly, this table represents all values over the whole unit circle. And when you plot those points, you end up with this thing, which looks very similar to the graph of the sine function. It's just shifted a little bit. And what you're going to see, I believe, on the next slide is a really neat animation that I lifted from. I really like the one, especially for sine on the bottom. So you can see the unit circle there in green. And what it's doing is it's tracing the point around the unit circle. And then remember that in the unit circle definition of the sine and cosine functions, the sine is the y value and the cosine is the x value. So when you take the sine values from the unit circle and use them to plot your sine function, it's the same y value. And that's why you can see, again, looking at the bottom of the screen, going from the unit circle to that red curve, that's making the sine graph. The cosine animation that you see up above that is not quite as cool. It's still pretty cool. The reason I say it's not quite as cool is because remember that in the unit circle definition, the cosine is the x value. Well, when you graph y equals cosine theta, they have to change that x into a y. And that's what you see happening in the top right corner there's nothing in that section except for on the bottom it's an x and they're translating it over into a y. Still pretty cool, but I really like the sine animation on the bottom. Some properties of the graph of the sine function. First of all, the domain is all real numbers, and you can see that from the graph because every x value is represented somewhere on the graph as you move from left to right. The range is only the closed interval from -1 to 1. There are no y values outside that interval. The maximum y value is 1. The minimum value is -1. The period is 2 pi, and again what that means is that when you go over an interval of length 2 pi, after that the graph is just going to repeat. And then this function is an odd function. We talked about that a few sections ago. And what that means in terms of the graph is that it has origin symmetry. It's symmetric with respect to the origin. So sine and cosine graphs have a few special features. The first one, so we're talking now about the graph of y equals a sine bx, where b is greater than 0. The amplitude is a measure of how tall the curve is. And the amplitude of y equals a sine bx is defined to be the absolute value of a. And what that has to do with the height of the graph, it's half the height of the graph, essentially. And you can see that in the picture. The period, so this goes back to chapter 1 where we talked about transformations. When you put a number in front of the x, what that does to the graph of the function is it either stretches it or shrinks it horizontally. So that number b is going to affect the period. It's either going to make it longer or shorter depending on how large the value of b is. It ends up that the period of y equals a sine bx is always 2 pi divided by b. So there are 5 basic steps to graphing a sine function. These steps can be very easily modified to graph a cosine function, and in the next section a tangent or cotangent function. So you're going to see these come up again and again. The first thing you want to do for a sine or cosine function is identify the amplitude, which is the absolute value of a, and the period 2 pi over b. Now, in order to get one period of the graph, we're going to make a table. And the way we're going to select the x values for the table is described here. We're going to set bx minus c, which is the expression inside the sine function. We're going to set that equal to 0. We're going to start the table there, and then we're going to go up in increments of the period divided by 4. And we're going to do that until we have a total of 5 x values. Then we're going to plug those 5 x values into the function to get the corresponding y values. Then you will have enough points to draw one full period of the graph. And if you're asked to draw more than one period, you can extend the curve to the right or to the left. So let's look at a couple of examples. Right after we talk about phase shifts. I don't use the phase shift personally too much when I'm actually doing the graphs. The procedure I just described sort of takes care of that. But I think in some problems they do ask you for the phase shift. So the phase shift just basically represents how far is the graph being shifted to the right or to the left. And so in the function y equals a sine bx minus c, the phase shift is c divided by b. And if that comes out to a positive number, the shift is to the right. If it comes out to a negative number, the shift is to the left. So now let's start looking at our examples. So our first example is y equals 2 sine 1/2 x. And they're asking us to graph that over the interval from 0 to 8 pi. So we'll go through our 5 steps. Number 1, we want to identify the amplitude and the period. So if you look at the number a, which is 2, the absolute value of 2 is 2, so that makes the amplitude 2. The period is going to be 2 pi divided by b, which is 2 pi divided by 1/2, which is 4 pi. So it's going to take an interval of length 4 pi to see one complete cycle of the graph. So the maximum value of y is 2, the minimum value of y is -2. That comes from the amplitude. So now we'll start making our table. So the first thing we want to do is set 1/2 x equal to 0. And that's how they get x1 equals 0. They're using x1 to stand for where it starts. And then we're going to add quarter periods to get all the values that we're going to use in the table. So the period divided by 4 comes out to pi, and so that means the 5x values that we're going to use in the table are 0, 0 plus pi, which is pi, add pi again, you get 2 pi, add pi again, you get 3 pi, add pi again, you get 4 pi. So our 5 values are 0, pi, 2 pi, 3 pi, and 4 pi. So now we're going to evaluate the function at those 5x values. At this point, you might want to pause the video and try to do this part yourself. Just plug those 5x values into the function and see what you get as the y values. So again, if you want to pause the video here and try to do that part. So now let's go ahead and see what we get. The formatting is a little funny on this. That box that you see between the 1/2 and the 0, that's supposed to be a multiplication sign. I will fix that one of these days. Anyway, the 5 points that we get are 0, 0, pi 2, pi comma 2, 2 pi comma 0, 3 pi comma negative 2, and 4 pi comma 0. So we're going to plot those 5 points. And when you do, and you connect them with a smooth curve, you get something that looks like this. Now remember, they asked us to graph the function over the interval from 0 to 8 pi. Right now we only have it from 0 to 4 pi. So all we're going to do is just draw that cycle one more time, going from 4 pi to 8 pi. And you see right here. Moving on to the next example. We're going to determine the amplitude, period, and phase shift of y equals 3 sine 2x minus pi over 3. And then we're going to graph one period of the function. Okay, so first the amplitude, period, and phase shift. Remember that the amplitude is the absolute value of a, which comes out to 3. The period is 2 pi divided by b, which comes out to pi. 2 pi divided by 2 is pi. And then the phase shift is c divided by b, so that's going to come out to pi over 3 divided by 2, which means the same thing as pi over 3 times 1/2, and that's pi over 6. So what that means is that this graph is going to be shifted horizontally pi over 6 units to the right. Now again, in the graphing procedure that I described a little earlier, we don't really have to use the phase shift. That kind of takes care of itself. Okay, so now we're going to find the values of x for the 5 key points. We do that by first setting bx minus c equal to 0. When you set bx minus c equal to 0, you get x equals pi over 6. And then we're going to go in increments of period divided by 4, which is pi over 4. Now, sometimes students get a little bit caught up in what happens next, because it's basically some messy adding of fractions. So we're starting at pi over 6 and going up in increments of pi over 4. So the next x value is going to be pi over 6 plus pi over 4. And in order to add those fractions, you need a common denominator, which is 12. So when you add those together, it's 2 pi over 12 plus 3 pi over 12, which is 5 pi over 12. And we have to add pi over 4 3 more times in order to get all 5 of the x values that we need. So I'm just going to go through that kind of quickly. Again, you can pause the video if you need to catch up on the details. It's really just adding fractions. So these are going to be our 5x values. We're going to start at pi over 6 and then go 5 pi over 12, 2 pi over 3, 11 pi over 12, and 7 pi over 6. Okay, so now this table did not all fit on one slide. You'll see it continue on the next slide. And again, I want to give you a chance to pause the video and try to evaluate the function at, well, at least these 3x values to start with, and then we'll catch up on the next slide with the 4th and 5th x value. So once you've tried that, what you should have, and again, remember that the box means multiplication. That's just a little formatting issue. The 5 points, or at least the first 3 points, are pi over 6, 0, 5 pi over 12, comma 3, 2 pi over 3, comma 0. And then remember, these are the last two x values. If you want to pause the video one more time and plug those in, give you a chance to do that now. Otherwise, we'll go ahead and look at those last 2 points. 11 pi over 12, comma negative 3, and 7 pi over 6, comma 0. So we're going to plot those 5 points and connect them with a smooth curve. And what you get is something that looks like this. And this time we don't have to do step 5 because they only asked for one period of the graph. So now we're going to start looking at some examples of cosine functions. It works very, very, very similar to how the sine examples worked, so these might actually go a little quicker. First, some properties of the graph of y equals cosine x. Just like sine, the domain is all real numbers. All x values are represented somewhere on the graph. And just like the sine function, the range is the closed interval from -1 to 1. The period is 2 pi, just like the sine function. Unlike the sine function, cosine is an even function. And you can see from the graph that this graph has y-axis symmetry. The graph of the sine function has origin symmetry. This is kind of nice because when you're graphing a cosine function, you don't have to worry about any negative values of x. You can just plug in positive values of x and then mirror it across the y-axis. These properties are, again, exactly the same as what you have for sine. The graph of y equals a cosine bx. The amplitude is the absolute value of a, and the period is 2 pi divided by b. And now this should look very, very familiar. To graph a function of the form y equals a cosine bx minus c, first you want to identify the amplitude and the period. And then in order to graph one period of the function, you're going to make a table. You're going to start the table at the value of x that makes bx minus c equals 0. And you're going to go in increments of period divided by 4 until you have a total of 5 x values. If this looks exactly the same as the procedure I described for graphing a sine function, that's because it is. It's exactly the same, no difference at all. So let's do it. Oh, first of all, again, this is exactly the same as what was described for sine, basically just the definition of the phase shift. And again, you'll need this if they ask you for the phase shift, but if they don't ask you for it separately, it's not something that you really have to find in order to draw the graph. It just happens automatically. Okay, so the first example is to determine the amplitude and the period of y equals -4 cosine pi x, and we're going to graph the function over the interval from -2 to 2. So first we're going to identify the amplitude and the period. So notice that a is -4. This is where you have to be careful. Amplitude is always a non-negative number. And so the amplitude of this function is going to be 4. The period is 2 pi divided by b, which comes out to 2 pi divided by pi, which is 2. So it's going to take 2 units to see one full cycle of this function. Okay, now we're going to find the values of x for the 5 key points. We're going to start by setting what's inside the cosine function equal to 0. To get the starting value, and that's going to give us x equals 0. Then we're going to go up in increments of period divided by 4, which comes out to 1/2. So that makes for nice numbers in this example. Start at 0. The next value is going to be 0 plus 1/2, which is 1/2. Next one is going to be 1/2 plus 1/2, which is 1. and then 1 plus 1/2, which is 3/2, and then finally 3/2 plus 1/2, which is 2. Okay, so this table doesn't fit on the slide. We're actually going to evaluate this function at 0, 1/2, 1, 3/2, and 2. Again, I would like to give you the opportunity to pause the video and try to calculate these y values yourself. Go ahead and do that now if you want. So now let's go ahead and look at what you get. First point on the graph is 0, -4. Second point is 1/2, 0, and then 1, 4. Here are the last two x values, and they give you points at 3/2, 0, and 2, -4. So when you plot those points and connect them with a smooth curve, you get something that looks like this. Now remember that they wanted the graph over the interval from -2 to 2. Let's see, they drew a little extra. What we got from our table would actually only go from 0 to 2. So to get it from -2 to 2, you just take that cycle that's going from 0 to 2 and repeat it, just extend it to the left one time. And you'll get something that looks like this. Okay, our last example is going to be to determine the amplitude, period, and phase shift of the function y equals 3/2 cosine of 2x plus pi, and then we're going to graph one period of the function. So using the 5-step procedure that we described earlier for both sine and cosine, and you're going to see a very similar procedure when we get to the next section for tangents and cotangents. First, we're going to identify the amplitude, period, and phase shift. The amplitude is the absolute value of A, which is 3/2. The period is 2 pi divided by B, which in this example comes out to pi, 2 pi divided by 2. And the phase shift is C over B, which is going to come out to be -pi over 2. Why is it negative? Because remember that the format of the function is y equals a cosine bx minus c, and in this example they have a plus. So instead of thinking of it as 2x plus pi, you might want to think of it as 2x minus -pi. And that means that the graph is going to be shifted pi over 2 to the left. So now we're going to find the x values. We're going to start by setting 2x plus pi equal to 0. And that's going to give us -pi over 2 for the starting value of x. And now we're going to keep adding pi over 4 until we get 5x values. -pi over 2 plus pi over 4 is -pi over 4. So you would need a common denominator 4 to do that. If you add pi over 4 again, you get 0. Add pi over 4 again, you get pi over 4. And add it one more time, you get pi over 2. So we're going to put in x values from -pi over 2 to pi over 2, going in increments of pi over 4. Okay, so this table is again spread over 2 slides. So one more time, I want to give you the opportunity to pause the video and try to get these y values by plugging in those values of x. So now let's check our work. First point is -pi over 2, 3/2. Then we have -pi over 4, 0. Sorry, it's spread over 3 slides. If you plug in 0, you get 0, -3/2. And then pi over 4, 0. And finally, if you plug in pi over 2, you get pi over 2, 3/2. Plotting those 5 points gives you something that looks like this. And that's actually going to be the end of the problem because they only asked for one period of the function, and that is one period. If you extended it to the left or to the right, you would just be getting additional periods. And that completes the video for section 4.5, graphing sine and cosine functions.